Yes, absolutely.
All right, I'm Chase Straw, Assistant Professor of Turfgrass Science. It's good to be here. This is Connor, or just got a new grad Connor, and I knew I was going to get him switched. This is Conlan. Conlan comes from Cincinnati, Ohio, right?
Yeah.
He's the only other Cincinnati Bengals fan that I know, like myself. So we're really excited that they're in the Super Bowl right now. I started this position 2 years ago, and he was my guinea pig. He's my first grad student. He's working on a master's. He came from the University of Tennessee. All of his background is in sports field management. So he did a lot of internships when he was at the University of Tennessee. Orlando, I don't know if this is the right order, Orlando FC, the Oval in London, which is a cricket pitch. And then also he worked for UT Athletics, correct? So lots of sports field experience, which fits in well with my program because I do a lot of sports field research. His master's work is a pretty unique project for a master's student. It's very interdisciplinary. We are collaborating with some folks over in the kinesiology department here, and he's looking at various athlete-surface interactions. So this is one of his 3 projects that he's going to present today. He plans to graduate in August, so these are very preliminary results. As you can see, he has a lot of data that we're trying to filter through, but he's doing a really good job with it. So let you take it from here.
All right, I'll get started. So rugby, soccer, and football, they all have something in common, and that's the surface they're played on, be it synthetic, be it natural, they're all played on some sort of surface. And we need to know how these athletes interact with the surface. And a lot of research has already been conducted comparing the synthetic versus natural. There's a study from 2019 looking at the rates of knee injuries on NCAA college football, where they found that higher rates of injuries occurred on synthetic turf. There was an MLS study also in 2019 that found that there was no difference between synthetic turf and natural grass. There's lots of studies out there that look at this between surface, natural versus synthetic, but that kind of misses a big portion of the field itself. So we're treating it as an entire unit. We want to look at, you see this field here? There's many different portions of the field. It's not uniform across the entire thing. It looks nice and pristine, but maybe if we took a mechanical testing device such as a Clegg hammer, which is a standardized method in the turfgrass industry, you get a completely different picture. There is a range, so you can just see the range there is 10, but the actual range goes past 20. And this is surface hardness, so that means when you impact the surface, the peak deceleration of the surface. And we took data at 100 points across this surface, and we noticed that this field is variable. It's the same field you saw here, but it's variable. So we see that these fields are variable, but there's not a lot of research out there that looks at what's the impact of this variability on athletes. And there's kind of a big reason why. How do you take variability within a surface and take it to a lab? Because up until recently, you had to go to like a kinesiology lab. And we can't get that level of variability in a lab. So through some preliminary research at UGA, they saw that injuries occurred in the areas of transition, mostly the volumetric water content transitions. And then further research was conducted at the University of Minnesota, which also saw performance-wise that the areas of transitions had differing levels of performance. So one of the great things about technology nowadays is it's allowed us to take stuff that's been in the field, been in the lab to the field. And this is through wearable technology. So like an Apple smartwatch is considered a wearable, a heart rate monitor is considered a wearable. And these wearables have allowed us to understand what the athlete is actually feeling at that specific portion in the field rather than being hooked up to a bunch of light bulbs that kind of use a mocap system to get the kinematics of the athlete. And one very popular example of a wearable is actually this torso worn GPS sensor. So this primarily will show us how far an athlete has ran, the speeds they reach when they run, the accelerations they do, the decelerations they do. So we get a lot more information from in the field rather than being restricted to a laboratory setting. So we kind of wanted to take this idea of using wearables and the idea that these fields are variable and to merge them and investigate the impact of this within field variability on athlete performance, specifically using the wearables. So this study started out with a institutional review board document where we got approval, and then we approached the rugby team, the first class rugby team at the university, and we recruited 19 members. And these 19 members were asked to come participate in the study. We used two different locations within Penn Berkeley. So the first location was and this is a Tifway 419 Bermuda grass field with a native sandy surface. It's mown to 19 millimeters and it's irrigated regularly. So it's well kept. We also had them come out another day and perform on this synthetic surface. This synthetic surface is an AstroTurf 3D3 with a styrene butadiene rubber, so crumb rubber, with no shock pad. It's regularly maintained, swept regularly, brushed regularly, and whenever there's any migratory crumb rubber, they refill it. So we're using these two fields and we're collecting a bunch of data. This data for the natural grass, some of these are more familiar than others. So normalized difference, NDVI, and volumetric water content. You guys are probably familiar with that. We also have rotational traction, surface hardness, vertical deformation, energy restitution, and force reduction. Rotational traction is simply a cleated foot that you rotate and you try to find when it breaks. You find the force that it breaks the surface. Surface hardness is the kind of the traditional method to quantify a field. It's used by the NFL. It's a 2.25 kilogram missile that you drop on the surface from 45.7 centimeters, and you measure the peak deceleration. Most notably, we used force reduction for the natural grass. That's the thing we were most interested in. For synthetic, we use a lot of the same, except we can't really use an NDVI sensor or a volumetric water content sensor because you're measuring stuff on a carpet rather than a root zone. So instead of volumetric water content and NDVI, we used infill depth. So simply you're measuring the length of the amount of infill to the backing. So typically it's 33 millimeters is typical value. To kind of describe a couple more of these values, vertical deformation is just how much the surface deformed from an impact, and energy restitution is the amount of energy that was returned to the athlete from this same impact. And then again, force reduction, I'll get more in detail about this now. Force reduction is the amount that the force that was impacted to the surface compared to a concrete control. So it's a relative measurement instead of an empirical measurement that like the surface hardness value is. This value is collected using this device here. It's a cylinder. It has a weighted 5.2 kilogram rated mass with it, and it has a spring on the bottom. And this is actually a well-used device by FIFA and World Rugby. World Rugby, since we're using rugby athletes, has a standard between 55 and 70%. So anywhere between that, they deem it an acceptable force reduction value. Just for an example, so a higher force reduction value, the more force reduced. So say you jump into a ball pit, that's going to have a really high force reduction value versus you jumping onto the tile floor here. So we need to collect a bunch of data across the field. We collected 195 georeferenced spots in the field. So they're all equally spaced and they all had a GPS coordinate with them. So this is kind of an overview of the process we did to handle the field data. So first we inputted the georeference data. It's ingested into ArcGIS Pro. Then we interpolated the data using empirical Bayesian kriging and then from the interpolation, we then selected the statistically significant hot portions of the field and statistically significant cold portions of the field. So the hard portions and the soft portions is a better way to think of it. And then it clusters it into zones. And then from these zones, we created zones and then uploaded it to a GPS that had plus or minus 50 centimeters of accuracy. One of the natural grass, turfgrass zones look like this. So for the hard zone, which is designated by the orange, had a force reduction value of 71.3%. The soft zone had a force reduction value of 76.4%. So if you do the math, it's kind of a 5.1% different range between the hard and the soft zone. So it's really not that much of a difference. On the day of the study, we went out with this GPS and walked the borders of these zones, setting up our activities. For the synthetic turf, we had an even less variability. So the hard zone had a force reduction value of 64.5%, and the soft zone had a force reduction value of 66.3%, which that range is 1.8%. Same method was used to walk the zones with the GPS before the athletes showed up on the day to designate our activity zones. So before I get into what activities these athletes performed, I wanted to talk about more of what we fitted these athletes with. So a big thing with any sort of athlete study is you have to control as much as possible. And one of the biggest source of errors is shoe-induced variability. So if athlete A was to wear one set of cleats and athlete B was to wear a completely other set of cleats, that could completely skew your data. So you have to control that. So we fitted these athletes with these cleats shown here. And as an incentive to participate in the study, the athletes were given these cleats at the end of the study. We also fitted the athletes with these little ankle monitors, which look like I forget the name right now. And these ankle monitors are 9 degrees of freedom. So they have a magnometer in it, a 16G accelerometer in it, and a gyro. On top of that 16G accelerometer, they also have a 200G plus or minus accelerometer with a 1600 hertz collection rate. The athletes were asked to perform 2 different agility activities. We had them perform in the order that I'm showing you next. All of the activities within the same field were performed on the same day. So that we did natural grass on day 1, and then they came back the following week and did synthetic turf. So the first activity we had the athletes perform is a drop step. So we had the athletes step off a platform from 40 centimeters and land on both feet. So pretty simple, pretty lightweight, but we had the athletes then repeat that 2 other times for a total of 3 replications. We also had the athletes perform a acceleration deceleration drill, which had the athletes accelerate as quickly as possible, 20 meters. And then once they hit that 20-meter mark, they decelerated as quickly as possible into a back pedal. Again, we had them repeat this twice for a total of 3 replications. So since we had 2 different zones, we had to segment them so athlete in a Latin squares type of randomization. So athlete A would start in the hard zone, and athlete B would start in the soft zone. After they completed all their activities within that same zone, they would switch. And for all the athletes we had them switch. So not one athlete started in the same zone each time to kind of reduce that learning bias and also the fatigue bias. Also, to reduce the fatigue bias, we had them do the easiest activity first, so the drop step. And then we had them do the hard activity. All of these activities followed by a required rest period, so to also further reduce the chance of fatigue bias. Athletes were also given a survey at the end of the session asking a variety of questions, including their perceived exertions from the section and their perception of surface variability. So kind of to get into the data analysis now, from the ankle IMU sensors, we had over 212 million rows of data, so that's fun to deal with. To deal with it, I had to use Python 3.10, and I extracted the peak tibial acceleration. So from those ankle sensors, I extracted the peak accelerations from it. For an example, here's the drop step. The y-axis is the accelerations in meters per second squared, and the x-axis, which is not really there, but it's time, and time increases. So we look for periods that have the peaks. So we're just looking for the peak accelerations there. So you can see designated by the X's, those are the peaks that were selected by the algorithm. For the acceleration, deceleration, we looked at the same thing. We were looking for the peak acceleration, and the graph is the same. So acceleration's on the y-axis and time is on the x-axis. So this is just an example of how we analyze the data. For statistical analysis, we used R 4.1.2, and we perform t-tests at alpha level equals 0.05. It's important to note that we did not compare across surfaces because of the variability of the variability. So we're only comparing natural grass to natural grass and synthetic turf to synthetic turf. So for the natural grass results, we'll look at drop step first. So on the y-axis is the peak accelerations, and on the x-axis is the different zones. As you can see, there's a significant difference. So P equals 0.04 was this value, and the hard zone was 16.9 meters per second squared higher than the soft zone. For the acceleration deceleration, there was no statistical significance. However, it is interesting to note that the hard zone had a greater range compared to, except for the bottom outlier, it had more variability. We also asked them on the day what their perceived best zone was. And overwhelmingly, over 80% of the participants said that the soft surface was the best zone for the day. Just for a reminder, the soft zones are designated in white and had a force reduction value of 76.4%. For the synthetic turf results, we're going to look at drop step first again. So it's important to remember that the synthetic turf was only 1.8% difference between the hard and soft zone. So these results are not statistically significant. And similar things were found with the acceleration deceleration. We did not see any significant differences. We attribute that to that lack of variability. I'll get in on that a little bit later. However, it's kind of interesting, even though we didn't see any difference really with the accelerometers, the athletes liked one zone a lot more than the other. The interesting thing even more here is that the fact that they like the harder surface for the synthetic turf rather than the softer. Synthetic turf was overwhelmingly more hard overall compared to the natural grass. So it's kind of interesting that they preferred the harder surface on synthetic turf. So to get a little bit into more of the perceptions we looked at, we asked them a couple other questions. I'm going to get into two of the ones that are more interesting. So first, we asked how they perceive the variability of the surface. And the diamond in this graph represents the mean, the line represents the median. And they perceived correctly, because the natural grass was more variable than the synthetic, they perceived the natural grass to be more variable. When asked about how they perceived the firmness of the field, they perceived again that the synthetic turf was harder than the natural grass, which aligns with the data that we collected prior to the agility trial. So in conclusion, for natural turf grass, we did notice difference, but based on the activity performed. Further research really needs to look at the different levels of variability. We were limited because we decided to use their home field. And when we took our field data, we realized that it was a lot less variable than we wanted. We were aiming to get a variability of the range of 55 to 70%. So we wanted one at 55 and one at 70%. However, that did not work out. We also had athletes perform different activities that I did not show here for lack of time. They performed a drop jump, so similar to the drop step, except they added a jump to it, and then a consistent speed jog. So that's all good and dandy, but what can we do about this? And I'm going to spend the next few minutes kind of talking about preliminary results from another one of my studies. So this study dealt with applying aerification to only half the 50% hardest area of the field. So we're only looking at half the field applying aerification. And we're looking for the control, we kind of see what you expect. No real difference. We kind of attribute the slight magnitude change to just differing levels of volumetric water content. But when we apply a blanket application, which is the traditional way to perform aerification, we don't change the spatial uniformity at all. We just change the magnitude. So the mean goes lower, not the uniformity of the surface. However, when we apply our precision application, so only aerifying the yellow, orange, and red portions of the field, we notice that we change the uniformity of the surface. Now, all of this is preliminary, but it is kind of interesting to see that this might be a way to influence the uniformity of a field. Now, before I conclude this presentation, I want to thank the co-authors, Dr. Strahl, Mr. Floyd, Dr. Thompson, and Dr. Riekman. I also want to thank the other committee members who helped me a lot with the aerification study, Dr. Seegers and Dr. Worley. And to conclude this seminar, I want to summarize kind of the findings I found. I found that the variability sometimes for natural grass mattered based on the activity they performed. So further investigations into the impact of sports field variability on athlete performance is necessary. And we need more levels of variability, be it the 2%, even though we didn't see any significance, maybe we increase the number of participants, be it 5%, or be it 25%, which we were ideally looking for, or other levels of variability between that. But it's also important to kind of look at how can turfgrass managers control this variability, because it's great and all if we can see that it impacts the athletes, but if we can't do anything about it, we need to, then it's not really of that much interest to us as agronomists. So it's important to adjust that so we can make a safe and high-performing field for all athletes, from recreational to professional. Thank you.
Questions? Conlan, great presentation. I was just wondering, how do you make differences between performances between different athletes versus the effects of the field itself? When you do a test, do you test between different athletes? Do you have like a population of variable performances, or are you just assuming that everyone performance is at its peak and then the effects that you're seeing are specifically because of the field?
So that's kind of why we have 19 people participating. So that's kind of,
Right, but I didn't showed any variability between the 19.
so you're trying to say that. So all of this is all of the different participants. So it's just shows all the participants in the box plot itself. So it's the variability of the.
Right, I was just wondering if there's any like effects of personal expressions over what any field. Have you ever thought of anything that could create a bias in your data?
So there are things, and we've kind of designed the study to mitigate those. So like the learning bias.
I know you put in the shoes, but
Yeah.
I feel like people themselves would also have a higher.
Yeah, so that's kind of why we did all the, like, we had the athletes come out on a single day and do just one field in a day rather than doing one portion of the field on one field and one portion of the other field. So if the athlete's not performing as well, they're not going to perform as well through the entire portion of the study.
Right.
Does that kind of make sense?
Yeah.
Yeah, so and that's also why we randomize. So one athlete would do one zone, then the other zone, because they could also learn more and perform better later on. So we randomized. So one athlete would do the hard zone first, and then they'd do the soft zone, and the other athlete would do the soft zone, then the hard zone. They had no clue. They just knew that it was a portion of the field. So I didn't even know the day of. I purposely blinded myself from knowing whatever portion of the field was what portion.
Know what the test was, period, like what they were, it was about field hardness or anything like that.
They knew that they were looking at field uniformity.
Okay.
And that's all they did.
Okay.
No. Yeah, because that would influence,
Right.
you'd presume that would influence them.
Did
So.
the athletes require the Turfgrass?
We did not ask any empirical questions about that. Anecdotally, because we had 45 minutes with each athlete twice, they would express how they like natural grass better. But I don't have any empirical data to back that up. It's only anecdotal.
Other questions? You know, you got to answer. You got to ask 3 questions, right?
Why do you think they liked hard? Was it the hard synthetic and a soft natural? Is it just because the experiences are like so different, like the playability is so separate?
So I could theorize all day on why. I don't know why, and I don't want to speculate
Okay.
because
I mean, you can, it's fun.
yeah, I know it is fun, but
Okay.
yeah, I don't know why.
Cool.
That's a very interesting question and one that needs to be addressed.
Other questions?
I think you got one in the chat. Second from the bottom.
No, it's just Julie saying, good
No.
job, everyone.
Do you think time would affect?
Oh, there is.
Yep. So,
Read the question.
yep. Do you think the time/weather conditions would affect the variability measures on the field? Yes, they would, because if you have a rainy day, your moisture level would be different versus a stretch of dry days, and that influences the force reduction values and the surface hardness values. So to kind of combat this, we did it right after we took the measurements. So we took it on a Monday, and then we had the athletes come out on a Tuesday, and we didn't have any rain events that happened between that period of time, kind of to combat that. variability.
So Conlan, you said that you didn't see significant differences here, right, between acceleration, decelerate, but you did in the acceleration. The one right before this one, you said those were significantly different or something.
The drop step?
Drop step, yeah.
So for the synthetic turf, we did not see any differences, but for the natural grass, we did see.
Okay, so at what point has there been any research where those differences need to be strong enough within a field to see actual like increases in injury risk? Like at what point does it become a significant issue for injury risk?
That's a good question because we don't know. And we're doing a lot of preliminary work trying to generate that idea because up until now, all the research has been done on a force plate in a lab. And being able to transition from a force plate in a lab to actual field, because you can't really grow grass on a force plate, it doesn't survive well. So you kind of miss that. We just don't have that connection yet of injury rates and actual forces.
Great job. Let's thank our speakers again.